Okay, so carrying on with our titration, we are now up to the point where we are going to be using 40 milliliters of sodium hydroxide. So we're still concerned with weak acid reacting with our strong base sodium hydroxide, and that's going to produce water and sodium cations in solution and our conjugate base in solution. We already calculated before that 40 mils of our weak acid contains 0.0100 moles of weak acid. Right? We're now to the point where we also have 40 milliliters of sodium hydroxide. Same concentration as the acid, so 40 mils of NaOH also contains 0.0100 moles of sodium hydroxide. So we have equivalent amounts of acid and base now. So within a titration, this is what we would call the equivalence point. It is the point where we have equal amounts of acid and base, where we've added enough base to completely neutralize the acid. So this is not a buffer anymore because we've exhausted all of the acid in our solution. That means we're going to have to approach the problem a little bit differently. Now, if you're doing a titration in lab, this is where you'd probably see a color change. You'd see maybe the change from a clear solution to a pink solution, indicating that you had added enough base to neutralize your acid, and then just a little bit of extra base is going to change the color of your indicator. Now, since these are the same, we won't have any of either left after the reaction. In fact, all of the weak acid will be converted into the conjugate base. So we'll have 0.0100 moles of A minus in solution. So no more acid. What we have now is just weak base. And if we have a solution that's just weak base, we know how to deal with that, or we should. We talked about that quite a bit back in the previous chapter. It's going to change the reaction that we're looking at. Now, instead of looking at HA, we want to start with our weak base. It's going to react with the water in solution. It's going to do what bases do. It's going to deprotonate the water to reform the weak acid. And that's going to leave hydroxide ions. Okay. With that equation, we can solve for the concentration of hydroxide using our ice chart, right, and then get from there to our pH. But here's a place where we've got to be careful. When we're looking at the buffers region, we didn't have to calculate concentration for HA and A minus, our weak acid and its conjugate base, because we could kind of extract that ratio of the how many moles of each we had. That's not the case here. When we start to fill out our ice chart, we need molarities. It's got to be in terms of molarity. So this value of moles we need to turn back into molarity before we can finish our ice chart. So if we have 0.100 moles of our weak base, we need to consider what is the volume of the solution at this point in the titration. We started with 40 milliliters of our weak acid. We've now added another 40 milliliters, so that would be 80 milliliters. That's 0.08 liters of solution. So if we divide 0.01 by 0.08, we get 0.125 molar, excuse me, is the concentration of this weak base solution. That is what we can start our ice chart with. Now, initial conditions, the reaction hasn't happened yet, so there isn't any product, just weak base. So we're going to lose some of the weak base, we're going to gain some of the products, the weak acid and the hydroxide ion. Right, so when we get to equilibrium, both of those will be X. Now here, we want to think about our assumption. Can we get rid of that minus X, or do we need to factor in that minus X when we're doing the problem? Right? And to do that, we want to compare concentration, so concentration of our weak base, and we want to compare that to the equilibrium constant. Well, the equilibrium constant we need is Kb, not Ka. Right? So we're also, when we get to this point in the titration, we need to calculate what Kb is. Now, you may remember Ka times Kb equals Kw, so we can calculate Kb by taking Kw and relating Ka to it. So that's 1 times 10 to the minus 14th divided by our Ka that was provided for benzoic acid, 6.3 times 10 to the negative 5th. Right? And plugging that in, we get 1.59 times 10 to the minus 10th. Okay, now for the assumption, 0.125 divided by 1.59 times 10 to the minus 10th, right? That's about 9 orders of magnitude difference, which means when we divide those, we're going to get a number in the order of 1 billion times difference between those two. And that means we can pretty easily ignore that minus x with a equilibrium constant that small, times 10 to the minus 10th. So at equilibrium, that'll just be 0.125. Okay. So from there, we can plug into our Kb expression. So Kb, again, products over reactants. I'm going to write it out since we have HA and OH minus now. The products and reactants have changed up since we switched reactions. But if we plug in there, 1.59 times 10 to the minus 10th, x for both of the components on top, 0.125 for the weak base. If we solve for x there, so 1.59 times 10 to the minus 10th, multiply through by 0.125, and then take the square root of that answer. We get x here is 4.46 times 10 to the minus 6th. And be careful, because that's not hydronium anymore. That is the concentration of the hydroxide ion, right? That's what we have in our equilibrium now. So if we take the negative log of that value, that's not the pH, that's the pOH. 5.35. Subtract that from 14 and we get the pH. So the pH equals 8.65. Now, this is particularly potentially troublesome when you're kind of following along. And if we look back for part C, our pH was 4.2. For part D, it was 4.68. So 5.35 actually seems like a pretty reasonable answer. It fits kind of right in with the trend of how the pH has been going up. Right? So it's easy to kind of fall into a trap and think, oh, I'm done, that's the right answer, it fits my trend. But we've got to remember physically what happened up here. We've now used up all of our weak acid. So we have kind of destroyed the buffer system by taking out the weak acid component. What we have now is a basic solution. A solution that has a base in it should have a pH above 7. So this is the one that should kind of ring a bell that it fits with the physical reality of what's happening during the titration. Okay, pretty long step. We'll do a separate video for part F.